Previous recommendation models mapped hidden taste factors by watching the crowd. Systems like collaborative filtering rely on massive networks of user behavior to find patterns in what we watch or buy. But if a brand new movie or song drops today with 0 views and 0 ratings, a crowd-reliant system cannot recommend it. It has no historical data to draw from. Here we see Algorithm 45, highlighted in our NLP and recommendation group, content-based recommendation. It is designed to solve this exact problem. How do you accurately recommend a piece of media using nothing but its own intrinsic traits? To evaluate a brand new item the second it is published, the system has to bypass crowd behavior completely and read the content itself. In the year 2000, a startup called Savage Beast Technologies, later known as Pandora, attempted to solve this matching problem entirely by hand. They hired 75 trained musicians to listen to tracks one by one. These experts manually scored each song on roughly 450 distinct musical genes, tracking specific levels of guitar distortion, the prevalence of a groove, or complex vocal harmonies. The output of that labor transformed a subjective piece of art into a rigid 450-dimensional feature vector. Every qualitative feeling the song evoked was fractured into hundreds of discrete, measurable data points. Pandora proved subjective taste could be quantified. But paying experts to hand-score millions of tracks is incredibly expensive. Modern catalogs require an automated mathematical approach. To automate this, we have to translate qualitative text descriptions and metadata directly into spatial coordinates. This abstract graphic shows how an entire collection of raw documents is pulled by an algorithm into a dense, multidimensional mathematical field. For text-based items, this extraction is usually handled by an algorithm called TF-IDF, or Term Frequency Inverse Document Frequency. TF-IDF scans the text and penalizes ubiquitous words like the or and. It then assigns massive numerical weight to rare distinguishing tags that make the item unique. Once an item is plotted as a vector of TF-IDF weights, a computer can compare it to any other item in the catalog without a human ever reading the description. This diagram shows the logic. In step 1, movies and their tags convert into numerical arrays. The matrix becomes a string of decimals. In step 2, liking the matrix establishes a user profile with that exact array. Step 3 scores every other item against that profile to generate ranked recommendations. The tool used to calculate these matches is called cosine similarity. Cosine similarity calculates the angle between two vectors, ignoring their magnitude. Because Blade Runner shares critical tags with the user profile, the vectors point in roughly the same direction, creating a narrow angle and a 0.67 score. Toy Story shares 0 tags, resting flat on the x-axis at a 90-degree angle, scoring 0. In a content-based system, a smaller geometric angle directly correlates to a stronger, more accurate recommendation. When you scale this angle measurement concept up from 3 items to millions of products, the math creates a map of relationships. This scatter plot visualizes that scale. Items with similar features naturally clump together into distinct, tightly grouped neighborhoods within the multi-dimensional feature space. To match a user to a new product, the system instantly calculates distances across millions of these coordinates. Finding the perfect recommendation at this scale is literally just a search for the nearest neighbors in a digital galaxy. This approach does have a structural vulnerability: the filter bubble. A system designed exclusively to find things exactly like what you already consume will only give you more of the same. It cannot surprise you with a cross-genre discovery. This comparison table highlights that weakness. Collaborative filtering finds unpredictable human connections because it watches what other people do, but it fails on day 1 for new items. Content-based filtering solves that cold start problem, but risks over-specialization. Modern platforms overcome the limits of both approaches by weaving the 2 distinct data streams together into a hybrid model. Content-based recommendation translates subjective human taste into a literal spatial direction, ensuring that even a brand new release won't get lost in the void. Now we have to translate this geometric theory into practice. We will write the Python code that turns a raw catalog into a ranked list. If we open the Chapter 12 notebook for this build, our starting materials are sparse. We load a dataset containing only movie titles and the text-based attributes attached to each, specifically genres and keywords. Here is the defining architectural constraint of this build. The machine has no access to human behavior. There is no matrix factorization, no user history logs, and no collaborative overlap data showing what thousands of other people watched. The engineering challenge is specific. We have to construct a functioning recommendation engine relying entirely on isolated item profiles. The first step in our Python pipeline brings in tfid IDF Factorizer. This tool scans the text descriptions and immediately applies a stop words filter, removing common vocabulary like the or and. TFIDF, see how sci-fi and cyberpunk get specific values. Executing fit transform pulverizes human language, rebuilding movie tags as an array of 0.6 coordinates. The result of this process is our TFIDF matrix. This is a sparse, multidimensional grid, where every row is a distinct movie, and every column represents one of those weighted vocabulary terms. Subjective human opinion is now absent. The item exists as a feature vector, a set of coordinates floating in mathematical space. To evaluate this newly created matrix, we import the linear kernel function from the scikit-learn library. This serves as the mathematical engine of our build. This formula shows cosine similarity. Linear kernel calculates the angle between feature vectors, mapping identical directions to 1 and unrelated to 0. Plotted, the matrix and Blade Runner share a small angle and high score. By running the matrix against itself, the code executes this calculation at scale. It generates an exhaustive item-by-item grid, mapping the precise angular distance of every movie to every other movie in the catalog. The core computational work of the entire recommendation system is achieved through this single line of linear algebra. To extract a usable output, we execute a query. We look up the index of a specific target movie, say The Dark Knight, and isolate its specific row of angular similarity scores from the grid. This ranked recommendation box shows what the sorting mechanism does with that row. The code takes the similarity scores and reorganizes the catalog in descending order, mapping the highest values, like the 0.67 for Blade Runner, to the top of the list. We then apply a final code slice to grab the top 10 results. We bypass index 0, which prevents the engine from redundantly recommending the target movie back to the user. The abstract geometry has been translated back into a human-readable, ranked list of nearest neighbors in feature space. We have successfully built a functional recommendation pipeline without consulting historical user interaction data. Functional code provides the foundation, but shipping a production system requires navigating deeper trade-offs. We have to determine where this purely item-based approach excels, where it traps the user, and when to integrate the behavior of the crowd. That's the real test. If you open any streaming app or digital storefront right now, you'll immediately hit the "more like this" rail. In the commercial software industry, the code powering these features isn't judged by whiteboard elegance. It is judged purely by its ability to survive in production, operating at a massive scale without breaking. The industrial workhorse behind many of these systems is algorithm number 45, content-based recommendation. It handles the heavy lifting for e-commerce similarity rails, newsfeed suggestions, and job matching platforms. Most people know collaborative filtering, which looks at what the broader crowd is clicking on. A content-based system, by contrast, ignores the crowd entirely. When user interaction data simply doesn't exist, this inward-looking logic is the only tool engineers have left to keep a catalog's inventory from vanishing into the void. To understand why ignoring the crowd is sometimes necessary, you have to look at the empirical data of any large catalog. There is always a severe imbalance between the blockbuster hits and the forgotten items. This graph shows interactions per item. That vertical spike represents a tiny catalog fraction capturing most attention. The flat line extending right is the long tail, where most inventory lives in obscurity. Collaborative filtering breaks down here. It requires user clicks that simply don't exist. To rescue these items, the algorithm has to stop looking at user behavior. Instead, it analyzes the inherent attributes of the items themselves. The long tail is exactly where a content-based recommendation system proves its commercial value, turning obscure inventory into discoverable assets. Before the algorithm can recommend an item based on its content, it first has to translate that media into a machine-readable format. Operating with total independence from crowd behavior provides a production team with specific engineering advantages. The first is solving the item cold start problem. Because the system only reads the item's own features, a brand new upload can be recommended the very second it hits the database. The second advantage is its immunity to niche tastes. The system works perfectly for highly specific, uncommon user preferences that the broader crowd would never interact with enough to validate. And the third is explainability. Unlike the black box nature of behavioral algorithms, a content-based system can explicitly tell a user exactly why an item was chosen, pointing directly to the shared tags. These three pillars grant an engineering team total control and transparency over their catalog, entirely bypassing the cold start void. But system architecture is an exercise in trade-offs. The exact logic that makes a content-based algorithm mathematically precise is also its greatest weakness. Because it only matches shared features, it creates a filter bubble, serving only more of the same content. It also relies on expensive, high-quality metadata. Finally, it fails the user cold start problem. A new user provides nothing to match against. In an environment where immediate user onboarding, surprise, and serendipity are primary goals, relying exclusively on content-based logic will cause user engagement to stagnate. That is why, at the scale of platforms like Netflix or Amazon, neither content-based nor collaborative filtering is ever deployed in isolation. Architects layer these algorithms together into a hybrid system, combining both philosophies to actively cover each other's blind spots. Content-based recommendation is used to safely inject new items into the ecosystem and provide explainability. Then, collaborative filtering takes over, processing the resulting behavioral data to provide the magic of serendipity. Content-based logic serves as the foundational bedrock of modern discovery. It guarantees that no item is ever entirely lost to the database. Algorithm 45, Content-Based Recommendation, is drawn from the book 50 Algorithms Every Programmer Should Know by Imran Ahmad. The second edition is available on Amazon and from Pact, with code and resources at neuralsca and the neuralsca channel. From 75 musicians scoring tracks by hand to matrix math ranking of global catalog, it remains the exact same quiet idea. Let the item speak for itself and recommend whatever points the same way.